Alright, so today I'm going to record a video on eigenvalues and diagonalization. Some of you have been requesting that, so let's start with a matrix. I'm going to start with an easy one. So 1, 0, 3, 0, 5, 0, 0. No, I don't want a 0 there. I'm going to do an even easier one. Well, if I do a 0 there, that's too easy. Let's do a still very easy, because it's going to be, this matrix is going to be symmetric, so it satisfied even better conditions. So let's call that matrix A, and let's say that we want to find the eigenvalues of that matrix A. To do that, what you do is you do the determinant of A minus lambda I. Now, what lambda I means is you're going to be multiplying lambda times the identity matrix that has ones along the diagonals. So when you subtract that, what you effectively are doing, you're subtracting lambda from each diagonal entry. So 1 minus lambda is going to be typed there. 0, 3. Let's hope 0. 5 minus lambda, 0. And then 3. 0, and then 1 minus lambda. A little bit crammed, but that's not the important part right now. We're going to compute that determinant anyway, so you'll see all the details. Now, in this case, you want to use cofactor expansion and expand your determinant along this row right there. Why would you do that? Well, because remember, the cofactor expansion starts with the entry of the matrix times a sign, and then times the determinant of the submatrix obtained by eliminating the column and row. And so if you have 0, when you multiply that term times 0, you don't have to compute the determinant, so it's one determinant less you have to compute. So in this case, the only determinant I have to compute is the one that corresponds to eliminating this column and this row. And I want to be using the 5 minus lambda. That is going to automatically become a common factor for my determinant, so I don't have to FOIL, and I end up computing the determinant or the polynomial of the roots of a quadratic polynomial. Alright, so what matrix do I obtain when I do that? By the way, I forgot to mention the signs. In this case, you would have plus, minus, plus. So this is going to be negative, plus. Or if you want to do it the formula, negative 1 to the power of 2 plus 2, that's the ijth position, and that's going to be negative 1 to the power of 4, so it's positive. That's why I don't have to add any signs there. Now, determinant of 1 minus lambda, 3, 3, 1 minus lambda. Now, the resulting matrix here without the lambdas is of the form A, B, BA. So when you, let me do a little parenthetical remark. When you have A, B, BA, you know that the eigenvalues are going to be A plus B and A minus B. Why would that be? Well, because you know the eigenvectors. If you multiply times 1, 1, you get A plus B, B plus A. So you get that the eigenvalue A plus B, or A plus B is an eigenvalue. And if you change this one for a negative, you get A minus B. Then you get B minus A, but that's negative A minus B. So A minus B is, again, an eigenvalue. A little remark can save you time, but we're going to expand it anyways. Now, from that comment, I would have that the eigenvalues here are going to be 4, 1 plus 3, and then 1 minus 3, which is going to be negative 2. So I know already my eigenvalues, but let's compute it anyways. So I will move over here in case I'm not able to fit everything where I have it. So 5 minus lambda. And then the determinant here becomes 1 minus lambda times 1 minus lambda is going to be 1 minus lambda squared, and then minus 3 times 3, so minus 9. Okay? Alright, so with that, I can then know that lambda equals 5 is going to be 1 root, and then I just have to FOIL this out and find the roots. So if I do that, I get lambda squared minus 2 lambda, and then plus 1 from this one, plus 1 minus 9, negative 8. Now it's just a matter of factoring it out. So what do I have? Lambda 4 and 2, so minus 4, lambda plus 2, And again, as we said, lambda equals to 4 from adding here and then subtracting -2. We already knew the solutions. One of them, let's call it lambda 1, will be 5. Lambda 2, let's call it 4. And lambda 3, -2. Did I fit that -2? Not sure. I hope I did. In any case, those are my eigenvalues. So I'm gonna move on. So that was the first part of my diagonalization, finding eigenvalues. Now I need to find eigenvectors, and this is the part that gets confusing to some people. So I'm gonna move my eigenvalues over here, leave myself enough room so I can compute everything cleanly. So let's go ahead, let me erase and I'll be back. All right, so now to eigenspaces. So the eigenspace corresponding to eigenvalue 5 is going to be the null space of the matrix A minus 5 times I. You're just replacing lambda equals to 5, and instead of determinant you're doing the null space. So again, you're going to be subtracting 5 along the diagonals. So this is going to be the null space of the matrix, and it's going to be 1 minus 5, -4, 0, 3. Now subtracting 5 here is going to be 0, 0, 0. This one we keep, this one we keep, and then we subtract 5 here, which is going to be -4. Now we find the reduced echelon form for this matrix, and this one is easy because you see these two are not multiples of each other, so both will correspond to a pivot, and this one is already 0, so nothing to do there. So it's going to be 0, 1, 0. Now you can still put that in your calculator or do your Gaussian elimination to obtain it. However, these ones usually turn out to be easy. Well, provided you start with such an easy matrix, I suppose. Anyways, once you have your reduced echelon form, you want to identify your free variables. And the free variable is going to be x2. Why? Because it doesn't correspond to a pivot. Now, I read my basis for the null space directly from here, but I'm going to go ahead and write the equations for you. So this equation, the first equation would be x1 equals to 0, because you're setting everything equal to 0. Then there's nothing for x2 in there, and then the next equation here tells me x3 equals 0. I should have left a little room for x2 because x2 is a free variable because there's no pivot there, so you're going to assign a variable to it. So now you can see that any vector that is in the null space of a minus 5i is going to be of the form 0 t 0, which means that this is going to be the span of just a single vector, and usually we pick 1. I mean, you'd be welcome to say 0, 1 half 0, but that would just really spite your professor. It really wouldn't help much. All right, but that's our first eigenspace. Now, how would I have done it? I would have identified that this is a free variable. I would have made this entry negative, but there is 0, so it would have been 0 here. Now I'm in the second column, so I would make that a 1 to represent that this is x2 equals t, and then 0 below. Once I pick this, everything below that would be 0. Anyways, let me do the next one, and we're gonna compute them all. I'm going to rate this for space sake. So I'll be all right. So now we do the next one. So v2, and I'm writing them in no particular order. Well, no, actually, take it back. I put them in non-increasing order, but that's preference. You don't have to do that. So this will be the null space of. I'm going to be subtracting now 4 along the diagonal. So that's going to be the null space of the matrix, and I'm going to be subtracting 4. So this is going to be -3, 0, 3. Now the next one will be 0, 1, 5 minus 4, 1, and then 0. And then the next one will be 3, and 0, -3. Now you see that here we have that this becomes the null space of 1, 0, -1 when I divide the row by -3. And then I get 0, 1, 0, and then these two cancel, so I get 0, 0, 0. So that one you can compute. So again, it's not too difficult to compute it. And I'm going to read it directly from here. Now, firstly, as I said, I identify my free variable. So my free variable now is x3 because I have pivot. And so this is going to be x3 is my free variable. And once I have that, I will write this as the span. Let me write it down here because I don't think I'm going to have enough room. So the span of just a single vector, because there's just one single free variable. The fact that that free variable appears at x3 is going to give me a 1 in the very bottom entry. And then what are my other two entries? Well, my other two entries are given by these two guys, because you see in each equation I would have x1 minus x3 would become plus. So you're just changing signs of each one of them. So I have a -1, I make it a +1. I have a 0, well, change sign, 0. And that gives me my vector that is going to be the one I'm going to choose for to span the eigenspace. All right, so I have enough. Possibly I'm going to have to save some steps here to find my next eigenspace. So V3, the next one I have, is going to be the null space of the matrix A minus -2i. So it's going to be A plus 2. I'm going to be adding 2 along along the diagonal. So let's go ahead and do that right away without writing everything, because I have just a little bit of room left. I won't have to erase anyways. I don't know why I'm rushing to do that. 3, 0, 3. And then the null space here, or the reduced echelon form, is going to be 1, 0, 1, 0, 1, 0, 0, 0, 0. And continuing as above, you get that this is the span of, and I don't know if I'm going to fit it, it's going to be -1, 0, 1. No, I didn't get to fit it. Oh well. So I'm going to write all the eigenspaces, and then we're going to do our diagonalization. So I'm going to write them down here, all of them together, and then I'm going to have this space. So I'm going to erase here, and I'll meet you in a second. All right, so now we have our eigenspaces. So we can put together our matrix P, with which we're going to diagonalize the matrix A, by just putting our eigen vectors as columns. So 0, 1, 0, the order does not matter, because if you just swap them, it's really not going to do anything. It's going to just permute the diagonal entries. So whenever you get your diagonal, it's not going to do anything. They're just going to get shuffled. But so don't worry about which order you write them. Now, you would compute P inverse here, but now, don't you hate when your professor always does tricks and says, well, I don't have to do it because blah, blah, blah. Well, I don't have to do it because I started with a symmetric matrix, and right here, this matrix is orthogonal, meaning that every vector is orthogonal to each other. So I know that the only thing I have to do is normalize it. So meaning I'm going to divide by the square root of 2 in every entry, and then I can get my inverse by just doing the transpose. So it's not going to be quite the transpose, but it's going to be quite close. So I'm going to go ahead and write it, and then we'll confirm. All right, so the trick is done. It took me a little bit longer because I didn't do a transpose, and I was thinking, why is it not working? Well, because I forgot the trick. But it's just a transpose, and then you have to normalize them. But anyway, so that's just because I started with a symmetric matrix. It does not always work that way. And then the only thing you'd have to now verify is that if you do P inverse A times P, and you can do that in your calculator, you're going to get your diagonal where the entries will correspond to the eigenvalues. And so you just have to be careful that in whichever order I pick them, and if I was careful enough, which I think I was, they would come out this way. Of course, whenever you plug it in your calculator to verify, you would actually get them in the right order. You don't have to even worry about the order. So anyways, that's how you do a diagonalization. And in fact, this is very close to an orthogonal diagonalization, which is the topic right after this one, after you do inner product spaces. In any case, that's what I have for you today, and I hope it's helpful, and I'll see you. Thank you for watching, and I'll see you in the next one.